Have you ever wondered how airplanes, those giant metal birds, manage to fly? It's a marvel that never ceases to amaze us. The idea of flight, of soaring through the skies, has captured our imagination since the dawn of time. This fascination led to countless attempts to conquer the skies, from the mythical Icarus to the more grounded efforts of inventors like Leonardo da Vinci. However, it wasn't until the turn of the 20th century that we finally achieved our dream of flight. In a small town of North Carolina, two brothers, Orville and Wilbur Wright, made history. On a cold December day, they launched their flyer into the frosty air, and for 12 glorious seconds they were airborne. Human flight was no longer a dream, it was a reality. From that moment, the world of aviation took off, quite literally. We moved from biplanes to monoplanes, from propellers to jet engines. The skies became our highways as we built bigger, faster, and more efficient birds of steel. Today, we have planes that can carry hundreds of passengers, flying at speeds that would have been unimaginable to the Wright brothers. Yet, despite the advances, the basic principles of flight remain the same. Every plane, no matter how large or small, relies on the same forces that lifted the Wright brothers off the ground. They need lift to rise into the air, gravity to stay grounded, thrust to move forward, and drag to slow down. It's a delicate balance, a dance of physics that allows us to journey through the skies. But flight is not just about the science. It's about the marvel, the magic that happens when a plane lifts off the ground, when it soars above the clouds, when it touches down in a far-off land. It's about the thrill of takeoff, the tranquility of cruising altitude, and the precision of landing. It's about connecting people, places, and cultures, shrinking our vast world into a global village. So buckle up as we prepare to take off into the science of flight. To understand how planes fly, you need to grasp four fundamental forces at play. Imagine you're at a park tossing a frisbee. The frisbee soars through the air, then eventually falls back to the ground. This simple action illustrates two of the four forces: lift and gravity. When you throw the frisbee, the shape of the frisbee and the air rushing underneath it create an upward force. That's lift. But gravity, as we all know, is the force that pulls everything down towards the earth. Your frisbee might fly high, but gravity ensures it doesn't escape into the stratosphere. Now, imagine you're on a bicycle. You pedal harder to go faster and ease off to slow down. This is a perfect example of the third force, thrust. In the case of an airplane, the engines provide the thrust, propelling the plane forward. But there's one more force to consider, the one that makes you feel the wind against your face as you ride your bike. Drag. It's the resistance you feel from the air as you move through it. For a plane, higher speeds mean more drag and more power is needed to overcome it. So how do these forces work in harmony? Well, when a plane is in flight, lift and gravity are in a tug of war. Lift pushes the plane up while gravity tries to pull it down. At the same time, thrust and drag are in their own battle. The engines push the plane forward with thrust, while drag tries to slow it down. For a successful flight, these forces need to be in balance. Too much lift or thrust and the plane climbs too high or goes too fast. Too much gravity or drag and the plane descends or slows down. It's a delicate dance, a ballet of forces, if you will. Now that we understand these forces, let's see how they work together to make an airplane fly. Ever notice the unique shape of airplane wings? There's a reason they're designed that way. Wings, or aerofoils, as they're technically known, are not just flat boards sticking out from the sides of a plane. They are meticulously designed and shaped to ensure that an airplane can take off, cruise, and land smoothly. This unique shape is crucial in creating something called lift, which is the force that opposes gravity and keeps the plane in the air. Now let's talk about how this lift is generated. Essentially, it's all about air pressure and speed. When air moves over the curved top surface of the wing, it travels faster than the air moving underneath the flat bottom surface. This difference in speed creates a pressure difference with lower pressure on top and higher pressure beneath the wing. This is where Bernoulli's principle comes into play. Named after the Swiss mathematician Daniel Bernoulli, the principle states that an increase in the speed of a fluid corresponds with a decrease in pressure. In the case of an airplane, the air is the fluid. So as the air speeds up over the curved top of the wing, the pressure decreases. Conversely, the slower moving air underneath the wing creates higher pressure. It's this pressure difference that creates lift and allows the airplane to ascend into the sky. But wings don't just create lift. They're also designed with various movable surfaces like ailerons and flaps, which allow the pilot to control the plane's direction and speed. For instance, during takeoff and landing, flaps are extended to increase the wing's surface area and generate more lift at lower speeds. And that's just the tip of the iceberg. The science behind wings is complex and fascinating, involving intricate calculations and principles of fluid dynamics, thermodynamics, and more. So, wings are more than just appendages, they are the heart of an airplane's ability to fly. If wings provide lift, then the engines provide the push. Let's talk about thrust. Airplanes are like birds, but instead of muscles, they use engines to generate power. These engines, whether they be propellers or jet engines, are the heart of the airplane, pumping out the necessary thrust to push the plane forward. Now, you might be wondering, how does an engine do that? Well, it's all about Newton's third law of motion. For every action, there's an equal and opposite reaction. When the engine burns fuel, it produces hot gases that shoot out from the back. This is the action. The reaction is the forward thrust that propels the airplane. Propeller engines, the kind you might see on a small private plane, work by spinning large blades that cut through the air. As the blades spin, they create a high-pressure area in front and a low-pressure area behind, effectively pulling the airplane forward. Jet engines, on the other hand, are a bit more complex. They suck in a large amount of air, compress it, and then mix it with fuel. This mixture is then ignited, producing a powerful blast of hot gas that propels the plane forward. This process is repeated thousands of times per minute, generating a continuous thrust, but it's not just about raw power. The efficiency of an engine is just as important. Modern airplane engines are marvels of engineering designed to provide maximum thrust while using as little fuel as possible. This not only makes air travel more cost-effective, but it also helps to reduce the environmental impact. So the next time you're on a plane, take a moment to appreciate the engines. They're not just big, noisy machines. They're finely tuned, incredibly efficient powerhouses that make flight possible. With lift and thrust working together, we are halfway through our flight. Now that the airplane is in the air, how does it steer and keep its course, you may wonder? The art of steering and maintaining the course of an airplane lies in the clever use of various control surfaces, primarily the ailerons, rudders, and elevators. Let's start with ailerons. These are small hinge sections on the outboard portion of a wing. Ailerons move in opposite directions. When one goes up, the other goes down. This causes the airplane to roll or bank into turns. The pilot controls the ailerons, and therefore the roll of the aircraft, using the control wheel or stick. Next, we have the rudder. The rudder is a hinged section at the rear of the airplane, on the vertical part of the tail. When the pilot moves the rudder to the left or right, it causes the airplane's nose to move in the same direction, controlling the yaw of the aircraft. The rudder is controlled by the pilot's feet on the rudder pedals. Lastly, let's take a look at the elevators. They're located on the tail of the airplane, on the horizontal part. By moving the elevators up or down, the pilot can make the airplane climb or descend, controlling the pitch of the aircraft. The elevators are also controlled by the pilot using the control wheel or stick. Now you might be thinking, that seems like a lot for a pilot to handle. And you're right, it's a complex task requiring skill and precision. But pilots undergo rigorous training to master the control of these surfaces. They learn to coordinate their movements using the ailerons, rudder, and elevators together to maintain a smooth and safe flight. And there's more. Modern airplanes are equipped with autopilot systems that can control these surfaces automatically, based on predetermined flight plans. Pilots monitor these systems and can take over manual control whenever necessary. So it's not just about getting into the air, but also about staying on course. And pilots, with their skills and the aid of technology, do this marvelously, guiding airplanes safely to their destinations. What goes up must come down, but how does an airplane land safely? Now let's turn our attention to the grand finale of any flight, the landing. It's a ballet of precision and control, a testament to human ingenuity and the power of technology. Imagine the plane as a giant bird, preparing to roost after a long flight. The first step in this process is for the pilot to reduce the airplane's speed. This is accomplished by reducing the engine's thrust and increasing the plane's angle of descent. It's a delicate balancing act as the pilot must maintain enough speed to keep the plane airborne but slow enough to safely touch down. Now, as the plane nears the runway, the landing gear is deployed. The landing gear, or the wheels of the airplane, are housed in the belly of the beast during flight. When it's time to land, they emerge ready to bear the weight of the plane and its passengers. This gear is more than just wheels. It's a complex system of struts and shock absorbers designed to withstand extreme forces. As the wheels hit the tarmac, they take the brunt of the plane's weight, cushioning the impact and providing a smooth ride for those on board. Once the plane has touched down, the pilot uses the brakes to slow the airplane further. But that's not all. The engines also play a crucial role in stopping the plane. The pilot can engage what's known as reverse thrust, where the engines are essentially put into reverse, providing additional braking power. Landing an airplane is an intricate dance, a symphony of science and skill. It's a process that requires an intimate understanding of the aircraft, the weather, and the runway. It requires split-second decisions, razor-sharp focus, and a steady hand. And yet, for all its complexity, it's a process that happens thousands of times every day, all around the world. It's a testament to the marvel of aviation, a testament to human ingenuity and the relentless pursuit of progress. Landing is a complex task, but with the right skills and technology, it's a smooth descent to the ground. Airplanes are a testament to human ingenuity and the power of science. From the moment they leave the ground to their graceful descent back to Earth, every aspect of their flight is a marvel to behold. As we've journeyed through the mechanics of flight, we've come to understand the integral role each component plays. The wings, for instance, are not just slabs of metal. They're carefully engineered structures that generate lift, the force that propels an airplane upwards against the pull of gravity. By altering the shape and angle of the wings, pilots can control the amount of lift generated, guiding the airplane's ascent and descent. Then we have the engines, the heart of the airplane. These powerhouses generate thrust, the force that propels an airplane forward. The engines suck in air, compress it, mix it with fuel, and ignite it. The resulting explosion creates a powerful force that pushes the airplane forward. The stronger the thrust, the faster the airplane can go. Controlling the flight is a symphony of coordination. Pilots manipulate the ailerons, rudder, and elevators, adjusting the airplane's direction and altitude. These control surfaces alter the flow of air around the airplane, causing it to roll, pitch, or yaw. It's a delicate balance requiring skill, precision, and a solid understanding of the principles of aerodynamics. And finally, the art of landing. This is where the rubber literally meets the road. Pilots must decrease speed, lower altitude, and adjust the airplane's angle of descent, all while maintaining control and ensuring a smooth touchdown. It's a challenging feat, requiring a combination of skill, experience, and a dash of bravery. Every stage of the flight, every component of the airplane, and every action of the pilot contribute to the miracle of flight. It's a perfect blend of science, engineering, and human skill, making what was once thought impossible, possible. So, the next time you see an airplane soaring high, you'll know exactly how it's defying gravity and making the miracle of flight possible.